Hey, hello, physics, let's see, 123 students. I wanted to do some examples for you. I think I mentioned in class today that we're just out of time, but there are 5 examples that have little techniques in each of them that I think would be good for you to see. So I'll let you make the call whether it's worth your time watching the video or not. But like I said, there's just some little subtleties that I feel like I should make available to you and you should see here. So let me just grab the hard copy of the book and look at number 17. And so 17 simply says this, that we have a 1 kilogram block of copper at 20 degrees Celsius, and it is dropped into a large vessel of liquid nitrogen that's at a temperature of 77.3 Kelvin. How many kilograms of liquid nitrogen boil away by the time the copper has cooled down to this 77.3 Kelvin? The specific heat of copper is, and the latent heat of vaporization of nitrogen is. So let's start with the basic idea here, that what I'm going to do is kind of imagine myself taking this container filled with liquid nitrogen. And so the temperature is very cold, as it said, 77.3 Kelvin. And so when I put something into it, and I'll just represent it with a little block here. I know a horseshoe doesn't really look like a block. But here's this copper. And what's going to happen, of course, is energy is going to come out of the copper and go to the nitrogen. Now, since the nitrogen is right at its boiling point, that energy will not raise its temperature, but will change it from a liquid into a gas. And I know it sounds a little funny because we often associate boiling with being something hot, but boiling is when it gets to the point that the molecular motion is enough to break the bonds and to break free. And for something like nitrogen, where there's very little bonds between the individual nitrogen molecules, it doesn't take much of a temperature for it to boil. And so that's why we're used to thinking of nitrogen as being a gas, because at room temperature it's already broken apart here. But here's what I'm getting at here, is there's going to be a Q for the copper, and there's going to be a Q for the nitrogen. And so it's coming out of the copper. So remember that our equations were based upon our system, if you will. And so if it is coming out of the copper, it's going to be a negative number. Remember, energy going in is positive, energy coming out is negative. Now, for the nitrogen, then, it must be greater than 0 because it goes into the nitrogen. And so kind of thinking those, copper as its system and nitrogen as its system. And here's the other nice thing, and this is why I picked this as an example problem, is I can then say the Q for the copper and the Q for the nitrogen, when you add them together, you're going to get 0. That's the principle of conservation of energy. One loses and one gains, and if it's in this insulated vessel, it is, gonna, what one loses, the other gains. Now, the copper is already a solid at room temperature, so when you cool it down, it just becomes, I don't know if you want to say, more of a solid. So its loss of energy would be mc delta T, where this all applies to the piece of copper. I think earlier I mentioned this being a horseshoe. This isn't a horseshoe. This is a block of copper. I think I'm thinking of your homework one. Yeah, number 7, where, it's a horseshoe and you drop it in water. Okay. That one's a little different too, by the way. I think that one, we want to know the final temperature of the water, and we ignore the amount that boils away. But nonetheless, the idea is still the same, that all the Q's would add up to be 0 there in number 7. Now, this other one here would be MLV, the latent heat of vaporization. So as it turns from a liquid into a vapor, this is where the energy would go, and this would be true for the nitrogen. And so we would have something that looks like this. And it's important then to recognize which term goes where. Otherwise, we might get these M's mixed up, like we might think they are the same. But this is the mass of the copper. So coming back to this particular problem, I'm going to put the mass of the copper as 1,000 grams. They said it was 1 kilogram, but if you'll notice later on, they say the specific heat is 0.092 calories for each gram, and for each degree Celsius it changes, or Kelvin. And so notice the specific heat is in grams, so I'm going to put my mass in grams. And the change in temperature, let's see, they said it started at 20 degrees Celsius. So if I put final minus initial here, the initial is 20 Celsius, but I'm going to write that as 293 Kelvin. And the final is 77.3 Kelvin. And so that's the change. And then notice it's a very big negative number. That's this part up here where I said this should come out and calculate to be a negative number. It loses heat. Okay. Which allows me then to change this degree Celsius to Kelvin. And so another thing I wanted to point out, and I've said it before, but it's worth saying it again, the change in temperature on the Kelvin and the Celsius are the same. So you can work with the changes on the Kelvin scale or the Celsius scale. It's kind of your choice. In this one, they gave us units of Celsius, so I kind of want to lean towards doing a change in Celsius. But they gave me temperature on the Kelvin scale, although they gave me this initial one on the Celsius. So it's kind of a judgment call. But I'm just going to switch everything to Kelvin. And that's justified because the specific heat is for each change in, and you can say change in 1 degree Celsius or change in 1 Kelvin. So even though they gave me units of Celsius, it's a change, so I can just change the unit of 1 degree Celsius to 1 Kelvin. Now, the other part of this equation, this would be the mass of the nitrogen that boils off. So we don't need to know this M in terms of the total mass of the nitrogen. That's not what's meant here. And of course, this M is not the mass of the copper. Don't confuse that. But this is the amount that boils off. This is the amount then that changes the phase. And so that is the question, how much actually boils off. And so that's what we want to be solving for. And then when they say the latent heat of vaporization, they say it's 48 calories per each gram as the units. And that's good because then my units for energy match on both terms. I don't have to convert from, a joule or something. And then that also means this mass is coming out to be in grams. Okay. And then anyways, that equals 0. So maybe I'll do something like this. It looks like there is going to be a gram that cancels off here, a Kelvin that cancels off there, and then this number should be in just calories. So I have 1,000 times 0.092 times 77.3 minus 293 close, and that should be my negative number. So negative 19844, maybe that's too many significant figures, but that's in calories. Maybe I'll move this one to the other side so it becomes negative 48 calories over grams with an M. I guess the negative would cancel off. I guess the calories would cancel off. And so to get M, I need to divide by 48, and then it would be in grams. So taking that number and dividing it by a negative 48 gives me a positive 413 grams, or 0.413 kilograms. Well, I probably don't need to do that. Grams is fine. They don't really say, yeah. Oh, it does say how many kilograms. How many kilograms boil off? Okay, that's what I was thinking. So last step is now to convert it into kilograms. How many kilograms of nitrogens boil away? All right, well, hopefully that was helpful. And like I said, a couple little subtlety tricks. I'll say them again. I wanted to point out that the sign of our thermodynamics, point out that it adds to zero or conservation of energy, and point out that a degree Celsius and a degree Kelvin are kind of that same idea. So let's move on to a little harder one. How about number 25? And see what it says here. And this kind of gets to the meat of this chapter, the harder ones, although 26 and 28 are a little bit better. But here it says you have 1 mole. So keep in mind that they're telling us how many we have or how much of an ideal gas, and it is warmed slowly so that it goes from some initial pressure and initial volume to 3 times the initial pressure and 3 times the initial volume in such a way that the pressure of the gas is directly proportional to the volume. Now let me pause right there, because what I wanted to say in this one is go ahead and do your PV diagrams. I like to say your PV diagrams, and there's other diagrams in thermodynamics, but for this introductory class we focus on the first diagram. But your diagrams in thermodynamics are important in like the free body diagram was so important in the mechanics. And so if you remember working out the mechanics problems, I would always say, okay, get a good physical picture first and then draw your free body diagram second. And I guess I'm saying the same thing. I mean, read it and get an idea physically of what's going on. And so, you know, I have some kind of gas, and maybe I'll say there's my gas in the container, and then it is warmed, and as it warms, it gets 3 times bigger. And interesting enough, not only does it get 3 times bigger, but the pressure goes up. Now, usually when something gets bigger, you think the pressure goes down because they're less concentrated. But if you warm it enough, then they go faster. So I would say this is really significantly warming it, because not only do we increase the volume, which would have a tendency to lower the pressure, we warmed it so much that the pressure actually then also went up by a factor of 3. And so this is not one of the ones we named in this chapter. We did isovolumetric, isobaric, isothermic, and adiabatic. And it's none of those. This is just a simple linear process. So on a PV diagram, it might look something like this. You have some initial volume and some initial pressure, and you go to 3 times that. So 1, 2, 3. So maybe 3 times the initial volume is here. 1, 2, 3. And maybe 3 times the initial pressure is here. And so the gas goes from here to here. Okay? Now, it also said that it did it in such a way that it's directly proportional to the volume. So directly proportional means it's a nice straight line. And so they give us the path. And let me take this as an opportunity to say that we know things like heat and work are path dependent. So we have to know where they begin and end, but we also have to know how they get there. So, like I said, this doesn't really have a path. I like to nickname it the Santa Barbara path, just because that's where we are. But in class, I'll joke with you and call anything that's kind of this straight line a Santa Barbara process, or maybe we have other processes. But not giving it a name is not really all that important. Now we finally get to the question. And the question is, how much work is done on the gas by this process? So keep in mind that we had said that the work can be easily calculated by the area under the curve, because the work is the integral of minus p dv. Actually, maybe I should say it's negative of the area. So the integral is the area with the minus sign here. So that's the amount of work. And likewise, keep in mind that we had said anytime something expands, now we talked about it during class as isothermic and adiabatic, but as it expands, it's pushing on the environment. The little demo I had in class lifted the weight up. And so the gas loses energy. And so no doubt this is going to come out to be a negative number. That's what I'm trying to say. So I'll have this area under here, and then I'll have a minus sign. Which, by the way, if it was a compression of the gas, I'd go the other way. And as you know, then when you change the direction of an integration, you get a minus sign. So you get a positive work, which is just the area when you compress the gas, and you get a negative when you expand the gas. So in our case, we're expanding it. It also makes calculating the area fairly easy because I don't really have to do an integration. The harder ones that we actually have to do the integration, and we did for the isotherm, we're kind of getting ready to do one for the adiabatic. And I said that mathematically is a little more challenge, and we need to talk a little bit more, and we will figure that out on Thursday. Okay, so I'll just take the area, and so in this case, if I do this rectangle down here, it would be the initial pressure, and that's the height of this rectangle, and the length would be 2 times the initial volume. Let me get the negative there. So that's the area of the rectangle. Now the area of this triangle above it, since it's a triangle, it's 1/2 the base, and the base is 2 times the initial volume, times the height, which is 2 times the initial pressure. So again, there's the negative sign, and so I'll just write that as 2 pi vi. And it looks like I also have another 2 pi vi. And so we have negative 4 times pi vi. And of course, we can't really give you a number. The general rule is when they give you symbols to work with, well, maybe I'll go back. The general rule is if they ever give you a problem and they give you numbers, you should plug in the numbers and finish the problem with a number. If they don't give you numbers and they give you symbols, you should finish in the symbols that they have given you. And clearly the symbols that they have given is initial pressure and initial volume. So I think we've answered that first part, how much work is done by the gas in the process. And another fun one to ask is B, how is the temperature of the gas related to its volume? And so we want something, that looks like mathematically this. Temperature equals what? And of course, temperature as a function of volume equals what? I think what they're really trying to say in this is pressure's not in this equation. So what I'm going to take advantage of is the PV equals nRT, and I'm also going to point out that what's really nice here about this equation is, remember, it works for all our processes. It works for the isovolumetric, the isobaric, the isothermic, and the adiabatic, but it also works for this Santa Barbara process, okay? So you might have something like this, that the initial pressure times the initial volume is then equal to nR times the initial temperature. You also might have something from this phrase that it is proportional here, is to say that we have a line on our PV diagram. And we know the equation for the line. So on the vertical axis, this is pressure. And on the horizontal axis, this is volume. The slope is the rise over the run. And so it's 2pi, that goes up here, versus a run of 2vi. And we can say that the intercept is 0 either by looking at this graph and projecting it back to the origin, or by saying they said it was proportional. Proportional means a line that goes through the origin, so that's got to be 0. But I'm going to say then I have a nice equation that connects pressure to volume, and this, of course, is the slope. And so really I have two sets of equations, and that's how I'm going to eliminate pressure here. See, because what I can do is then come over here and replace pressure in this equation with nRT over volume. And then I have initial pressure over initial volume times the current volume. And of course, you can kind of see that if you talk about the initial conditions, right here, this would be initial volume that would cancel off. And then, of course, you would have initial pressure. And then, of course, if you put in your initial conditions, initial temperature, initial volume, this would give you initial pressure. So it's matching. Initial pressure equals initial pressure. But the point here is I don't have pressure in the equation anymore. I have temperature and a bunch of constants. So let me put my constants all together, starting with the one that comes from the slope, and then I will then divide by the nr. And then I'll bring the V over here and I'll group it together, and volume squared. And I think we are safe because it said 1 mole. And so I have initial pressure over initial volume times R is then times volume squared. And so this is the part that I was saying, that the temperature is going to go up dramatically. So in other words, we increased the volume by a factor of 3, and it's 3 squared. So what's going to happen is the temperature is going to go up by a factor of 3 squared, which is 9. So for this to work, and the reason it works is when you warm it, not only does the volume get bigger, so the volume gets bigger by a factor of 3, which if the temperature got bigger by a factor of 3, that would just keep the pressure the same. But there's another factor of 3 increase in the temperature to make the pressure go up by a factor of 3. So there's 2 factors of 3 that are necessary to make the pressure go up and the volume to go up. And so not a surprise that it goes up by this factor of V squared. But that's the equation you will have. It's when it says, how is the temperature of the gas related to the volume? It's a quadratic. So you can say temperature is proportional to volume squared, if you will. And I suppose we could even rearrange things using this information. But I don't see any advantage in that. All right, well, anyways, hopefully that illustrated a couple of nice things. And so there's number 2025. So there's the second one I wanted to show you. All right, so let me move on then to number 26. All right, so 26 looks like this. It says a gas is taken through a cyclic process. So cyclic process means it goes all the way back where it started. So I'm glad they gave me a PV diagram here, and it is described by this figure. So it looks like it first goes from A to B. I'll call that the Santa Barbara process. But then as it goes from B to C, that would be a constant volume. So that's the isovolumetric we talked about. And then it goes from C back to A, and that's constant pressure. So that's the isobaric, and it's in a compression of the isobaric. So a gas is taken through the cyclic process as described. Find the net energy transferred to the gas by heating during one complete cycle. Okay? If the cycle is reversed, that is, the process follows the path A to C to B back to A, what is the net energy input per cycle in heat? Okay, so what we have here is a chance for me to kind of say, maybe I can break this down in a process from A to B, B to C, and C back to A, okay? And what I wanted to show you in this one, and in the next one here, is I like to make this little chart that basically has the first law of thermodynamics, which says the change in internal energy is equal to the work and then any heat. So in this first column, I'll do change in internal energy. The next column, I will do work. And the next column, I'll do Q. Now, I'm not so sure they've given me enough information to do every step, and I'm not sure I need to. Looks like this red one keeps smearing. What if I switch over to a little better ink here, the blue one? But what I do want to add is what I would call total. And I want to take this as an opportunity to say that the work and the heat are these path dependent, and depends how you get there. So we've got to look at every path and see how it got there. But at a delta E, you do not. And the reason that's important, and I kept saying that we're going to appreciate this state function, is I can then say the change in internal energy of this gas is 0, because the gas gets back to where it started. It started at A, did a bunch of stuff, and returned to A. And if it's path independent, if it's a state function, when it gets back to A, I know it has the same internal kinetic energy. Because at A, it has the same pressure, the same volume, and the same temperature that it started at. And so, whereas I may not know what the change in energy is for each individual step, the big thing I wanted to show you was the cyclic process tells me right away that the change in internal energy is 0. Again, this is why I made such a big deal out of non-state functions and state functions. Things that we got to pay attention to the path, and things that we don't have to pay attention to the path. See, what this is saying here is whatever the total work is in this box, if I did them individually, I'd get a total. And if I did the Q's individually, and I have to do them individually to get the path, but adding them together, I'd get a Q here. But what I'm really trying to say is these two numbers must be equal in magnitude but opposite in sign for these two to add up to 0. And so when they tell me in this question to find the net energy transferred to, so net energy. So they want to know the total energy transferred to the system by heat during one complete cycle. So they want to know this. This is really what is being asked of me. And what I call the front door approach is to find out the Q at each step and add them together. That's kind of my first reaction. Said, okay, well, just find it out for each one, and I got to do them separately for each one because they are path dependent. and then add them together. That's going to give me the total. But a backdoor approach is to say, what if we found the work for each cycle here and added that together? Whatever we got there must be equal in magnitude but opposite in sign to that one. And so that's the backdoor approach. And since we've got a nice PV diagram that has straight lines, and we know the work is the area under the curve, this one sounds very inviting to me. And so I'm going to come over here and say, okay, so A to B, the area under the curve would be this triangle and actually this rectangle underneath it. Then if I go B to C, there is no area under the curve. Maybe I shouldn't even waste time putting that in here. But what I really want you to see then is as I go from C to A, the area under the curve being negative would subtract that off. And so the net area is this highlighted triangle. This highlighted triangle would be that total. So I could say work net is equal to negative of the area that is enclosed in this little cycle. Because this right here, as I said, A to B would be a triangle plus the rectangle. And C to A would be taking away the rectangle. And so the only area I need is the area of that rectangle. Okay, so putting the negative sign out in front and now calculating the area, it's 1/2. And the base is from C to A or A to C. And it looks like it goes from a 6 to a 10. So that's a difference of 4 cubic meters. And then the height, and maybe I'll put the diagram back in the screen, but the height here is a 4 to an 8. So that's a 6 kilopascals in height. And this is the 4 cubic meters in base. Then height is 6 kilopascals. So I'm going to put 6. And instead of putting kilo, I'm going to put 1,000. And I'm going to put a Pascal. All right. So calculating all of this, I guess a 4 and a 2, 1/2 make a 2. 2 times 6 is a 12. So this is 12,000. Let me not forget the minus sign. And as we get more familiar with this, keep in mind that a cubic meter times a Pascal, which is a Newton per square meter, would then cancel 2 of them, and then you would have a Newton times a meter, which is a joule. And so this is negative 12, and I don't know if you want to write it as a 1,000 joules or a 12 kilojoules. And so notice this is a negative number. Therefore, Q net must be negative of work net. And I'll say it again, why? Because, again, we returned on a cycle. We returned back. And so that's 0. So that plus that has to equal 0. So the heat added must be at 12,000 kilojoules. And just to give some physical interpretation of this, I hope you kind of caught the idea that what we essentially did with this gas is we put heat into it, kind of like burning gasoline. And we got a net work out of it. So negative 12 kilojoules came out of our gas. And presumably then went to the car if this is an internal combustion engine. We deliberately made heat, and so we have a heat engine. That's why we call it a combustion engine. We actually burn something, and it's internal because we burn it inside a cylinder, unlike other engines that are externally burning. Not very common anymore these days, but like the Stirling engine and the steam engine, you have all the combustion outside and you make the hot steam and then you pump it in. So those are all external combustion engines. So this is well, actually we don't know if this is internal or external, but all I do know is I've put heat in to my cycle and gotten work out. And that's the idea of an engine. This is what comes out. So this would be now making my car go faster. I burned this gasoline and made the car go faster. All right, so I hope that adds a little insight to our diagrams. And we're starting to get enough thermodynamics that we can start to see how this is going to work in practice, and how we're going to actually then talk more about rotary engines, internal combustion engines, diesel engines, and the thermodynamics behind them, and a little bit of the mechanics, because to understand the mechanics, we got to get into, or to understand thermodynamics, we got to get into the mechanics a little bit and understand them, but that's not really the design here. It's not an automotive shop class. Okay, so let's see. I guess that's the third one in my example list. Okay, let me move on to number 28. And 28, again, is more of this PV diagram. And I think it, too, has a cycle. Yeah, I see the diagram here. I guess it starts down here. A sample of an ideal gas goes through a process shown in the figure. From A to B, the process is adiabatic. So maybe I'll see if I can get the whole page into the screen. Okay, so A to B right there, they say from A to B, the process is adiabatic. And then from B to C, it's isobaric. And then they tell me a little bit about the energy. 100 kilojoules of energy enters the system by heat. That's the Q. C to D, the process is an isotherm. And from D back to A is isobaric with 150 kilojoules of energy leaving the system by heat. Determine the difference in internal energy as we go from B, we go from A to B, so it's final minus initial. So what is the change of internal energy? And of course, this is the harder adiabatic one. But what we're going to do is kind of a backdoor approach and say that if we go in a whole cycle, the change in energy is zero. So if we get the change of internal energy of the other three, the ones we spent more time focusing on, we can then get the unknown adiabatic. And of course, like I said earlier on in this video and also in class, we're going to talk about the shape of this curve from the adiabatic one. And we can actually do a front door approach once we do that, but we don't have that skill quite yet to do a front door approach. All right, so the reason, again, I picked this as an example is this gives me a chance then to point out what I was saying before. I like to make these little charts, A to B, B to C, C to D, and D back to A, and then total. And I like to list the delta E first because that's the one that is, path independent and usually a little bit easier to do. It doesn't really matter which one is next. I just have gotten kind of in the habit of putting a work and then a Q. Now, we do know that for the whole cycle, it's zero. So that's the argument we just did on number 26. And I'll say it again, it's path independent. So if you leave A and you go through this whole cycle, A to B, B to C, C to D, back to A, you're going to be back here to the same pressure and the same volume as before. Okay? And because of that, you are going to, know that the whole change is a zero. And that's as I said, my backdoor approach, because I'm wondering if I can figure out the delta E from A to B and then B to C and then, A to B is what I'm looking for, okay? But if I can then figure out the B to C, the C to D, and the D to A, knowing that all four of them have to add up to 0, getting these three would really help me with the one I want to get. Okay. And if I come back and go to the reading here, they make it very clear that this process, the B to C, is isobaric with 100 kilojoules of energy entering as heat. So I'm going to put over here a plus 100. And of course in the units I'll just put kilojoules. So that's what they said. Maybe I'll grab this back up here, right? Where was it? Right here. So from B to C, it's isobaric with 100 kilojoules entering as heat. Because the other nice thing is the work from B to C is also known because it is minus the area under the curve. And so if I go work, and from B to C, it's minus the area under that curve. Now, it shouldn't be a surprise that the work is going to come out to be a negative number. We've talked about this a few times. I'll say it again. Anytime the gas expands, and so B to C is going along an increase in the volume axis, and so anytime it expands, it does work on the environment. It's pushing on the environment. The gas has to give up its energy in order to do that. And that means its temperature could go down or not if you add energy to it. And so we're adding some energy here. Is it enough to make the temperature go up or stay the same or still go down? I don't know. But let me just figure out the work. And so if we come back to this, we have a little rectangle. And it looks like C has a volume of 0.4 and B has a volume of 0.09. So there's the change in the volume, and the pressure is 3 atmospheres. Ooh, so let me be a little careful with my units here. This on the axis, the volume axis, is cubic meters. That's good. But I'm a little thrown off by the vertical axis because the vertical axis is in atmospheres. And so this area under the curve here is 3 atmospheres, but it's converting into pascals would be times 101. And maybe I should convert to kilopascals. So this is 3 times 101.3 kilopascals. And that way, when I go to calculate my work here, I'm going to have a kilo here, and then I will have a cubic meter and a pascal. And as we just did in the last problem, that's a joule. And so there's my negative. And so sure enough, I expect to get a negative. Okay, so let's see. I've got the 0.4 minus the 0.09 enter. And then times a 3, and then times 101.3. And so this would be a 94.2. So I'll put it in this little box. 94.2 units are kilojoules, and it's negative. And so it looks like a little more heat was added than taken out. So this temperature is going to go up a little bit, but probably not by too much. But the big thing here, like I said, is I'd like to know the delta E here, here, and here, knowing that I can then get this one. And so this is great because 100 added to a negative, let's see, 95 makes 5.8. So this would be 5.8, and it would be plus in units of kilojoules. So there's a small net gain of internal energy in this B to C process. All right, let's keep talking. C to D. Well, C to D is an isotherm. And so isotherm means the molecules don't go any faster. We could get out the equation we derived for this isotherm for how much work and actually get the work. And then we can also get the formula for the heat, and we'll see that they calculate to be equal and opposite. And so I add them together, I get 0. In fact, that's how we got the equation. We implied that the change in internal energy for the isotherm is 0 because the molecules don't go any faster. That's the only place energy can go in a gas. And so when you say you have a constant temperature, they don't increase their kinetic energy. That is, their internal energy is only kinetic. So there's no point in calculating either of those two. I can just jump right to the one I really want. By the way, I guess I should have said there's no point in calculating these. I don't even have the equation yet. We'll derive those soon. But I'm not going to do those to figure out this. That might be a front door approach. I'm going to say, let's get these other ones and then figure out what that one is. Which is really nice because D back to A is another isobaric. And in this case, it's negative of the negative area, if you will, because the work is the area under it, or negative of the area under it. And now this time we're doing the integral in the opposite direction. We're compressing the gas. And so from D to A, we are squeezing the gas. We're doing work on the gas. And so we expect to get a positive number here for the work. And so it would be just the area. Because they said from C to D, the process is isotherm. But from D to A, it's isobaric with 150 kilojoules leaving the system. So they directly tell us that this Q is 150, and because it's leaving, they told us it's a minus sign. And that's the other little subtlety I wanted you to see. Remember, we started our thermodynamics saying energy that goes in is positive, energy that comes out is negative. Not all textbooks define it that way, by the way, but that's how this one does it. And so that number's negative, so it's coming out. And it kind of makes sense because we are also putting in positive work. We're squeezing the gas, so this should be a positive, and it should be the area here. So coming back to my graph here, the area under this A to D line, it looks like the base of it is 1 cubic meter in the x-axis and 1 atmosphere on the vertical. So this would be 1 cubic meter times 1 atmosphere, but a 1.03 kilopascals. And that's, I guess, pretty easy math. That's going to be kilo there, and the units come out to be joules, and 111 is then 101.3. And so this is plus 101.3. Okay. And that should give me enough to complete the problem, although I probably will say one more thing. So let me just take my 101.3 and subtract my 150. And so this loses a total energy of 48.7. Now, hopefully that kind of makes sense here, because the first part of it read that you're taking this much heat out. And a naive answer would be to say, oh, well, that's how much came out. 150. No, because as you were taking 150 out, you were squeezing the gas. You were doing work on it, so you were adding this much energy back, and so this is the net change. And like I said, that's enough to finish this problem, but I probably should have come back here because I probably carelessly quickly just put an X here saying, oh, we don't know that, we don't need it. But the truth is we do know this Q, and this would be kind of a good time to remind you that the Q is 0 for the adiabatic process. Now, again, not that we need it, but that could be very helpful. You see, I'm about to finish this problem by realizing what that is. But you see, once I have that one, I can then put it here knowing that's 0. And once I have that one, I can then, well, it'd be a two-step process. But knowing that these would be equal and opposite, these got to come out to be equal and opposite. And so is that enough to solve it? I think so. So we could actually finish in this whole chart, but we don't need to go that far, and this video is getting long enough here. And really what I wanted to show you, I am showing you, and that is how these things play together, how you can say, I'll do a front door approach to get this, and I'll find these two and add it, or I can do a back door approach knowing that all of these add up and give me a 0. All right, so to finish this, let me take that negative 48.7 and then add to it a 5.8. And so all of this together is a negative 42. So this should be a positive 42.9. Which, by the way, notice it's a positive. And that hopefully makes sense, because during this adiabatic process from A to B, we're compressing the gas. When you compress the gas, you do work on it. You do positive work. And so we come here to this picture, right? From A to B, we're compressing it. And so positive work from A to B, but C to D, we're expanding it. And that should then be negative work. B to C should be an expansion, negative work. But D to A is a compression. Okay, so there's positive work. So positive work, negative work, positive work, and I guess that work, because it C to D expanded, that would be then a negative. Okay, anyways, I think we've answered the question on what might be the hardest one and maybe the main one I wanted to show you. And, oh good, looks like I might make it under an hour. All this chit-chatting. And let's go and do the last one on my list. And again, hopefully all these will give you the little skills to get through this chapter and the next beyond that, because learning these little tricks is powerful. And that's what I want you to see. So we'll play a little puzzle. We got a little chart that we have to fill in. That's how I kind of like to describe it. So the last one, a little bit different, because if you remember, we did some thermal conductivity one, and that's what this one is about. Maybe this is a hot water pipe, and the heat is coming out. Maybe it's a water heater. Water heaters are kind of a cylinder shape also, and so the hot water, the heat, comes out. But let's look at this. It says here, here's the picture, but here's the question. It says the inside of a hollow cylinder is maintained at some temperature TA, while the outside is at a lower temperature of TB. And then they say, look at this figure. So again, maybe this is a hot water heater. The wall of the cylinder has some thermal conductivity called K. Ignoring the end effects, so in other words, heat would come out the top and the bottom also, but just kind of imagine it's a long hot water pipe, so the edges aren't significant. Ignoring the edge effects, show that the rate of energy conducting from the inner side to the outer surface in a radial direction is given by this equation. So we got a little bit of calculus to do. Let's start off by kind of setting this up. You might remember that we had this equation for the thermal conductivity. The rate of flow is equal to K times A times the temperature gradient. And now I just realize I might not have put a minus sign there as we were talking about it in class. The reason the minus sign is important is because if you have a hot object and you put it near a cold object and you connect it with those conducting rods I was talking about, the energy flows from the hot one to the cold one. But the gradient, if you will, is actually, pointing or angling from low to high. So that's how the temperature changes with X. And the energy flows from hot to cold. And so what we need to say is the flow is opposite of the temperature gradient. And so this temperature gradient is going, in my picture, from the right to the left. This is how the temperature changes with position. It's an increase that way, which, of course, energy flows opposite. So I'm not sure if I included that negative. I don't think I did. I know the book had it, and so maybe I should flip back to the book here. Looks like the book, at least in the summary, puts the absolute value of the temperature gradient. And maybe that's the only way he writes it, so he never writes it with a negative. And I suppose that makes sense. A lot of time that's all we care about is how much. It's obvious which way it's flowing. It's flowing from hot to cold. But I'm going to leave the negative in my equation here. And so let's talk about the difficulty of solving this problem, because what I have, and I'll make kind of the inner cylinder right here. And so this is hot. And the energy is going to be flowing outward in a radial direction. So I guess from a top-down view, I'd have a circle, and the energy is going to be flowing outward. And if this is a water heater, it's usually wrapped in insulating material. Most water heaters come with an insulating blanket between two metal pieces, so it's kind of hard to see the insulating blanket because you see the outside wall, but if you could cut it, you would see a bunch of styrofoam and insulating material, and then the container inside. And some people, even for extra, will go buy an insulating blanket and wrap it around the water heater, so the water heater is even more insulated. Especially since many water heaters sit in the garage, and the garage can get cold. Not so much in Santa Barbara, so it's not really worth it in Santa Barbara. But if colder environments, this would be, cost effective and worth your time to have more insulation to it. Although maybe when you buy them, they come with more insulation than Southern California anyways. Anyways, if I kind of break this down into layers, which is my red marker, I could say the energy's got to flow through one microscopic layer and another microscopic layer and another microscopic layer and another and another. And so let me just take this microscopic all the way around. And so if I try to apply the equation here to kind of this cylinder going out, I'll leave the dq dt alone for a moment. I'll even leave the area alone for just a moment. But this right here would be how the temperature changes. And I might just change the variable to a radial direction. And that might be the first major step, is to recognize that this was derived and thought about as heat flowed along the x-axis. But heat doesn't always flow along the x-axis. It can flow along some other mathematical parameter, and then this would be radial. So I'm going to change that to a temperature change per radial direction. And so each microscopic layer then, because of conservation of energy, if the hot water is kept at a constant hot temperature and the cold is, some outside cold temperature in the garage, then the flow of energy is stable and the same for every layer. And so a little bit of energy flows through the first layer, and then that flows to the next layer and the next layer and the next layer, because if it didn't equal in every layer, one layer would start to warm up. And that's what would happen at first. I mean, if you had an empty water heater and you poured water into it, it would have to start warming up the insulation. And this insulation here near the hot water would be warmer than here. In fact, there would be a whole temperature gradient going from the hot water to the cold. But once we reach what we would call a equilibrium condition, it would be more described as a dynamic equilibrium position, each layer of our blanket wrapped around it, and so these microscopic cylinders that I'm picturing in my mind wrapped around it, would be at some temperature and they would stay there. And so whatever energy flows in, flows out. So I'm going to use that to my advantage to say, number one, the energy flows in a radial direction. And so I'm looking at a temperature gradient in the radial direction. And number two, I'm going to say every little piece that I wrap around has this same value. And so I'm going to think of this as being a constant. That's going to be very important when I begin to do my calculus. Now, the area would be this area wrapping around. And if you can imagine a microscopic, cylinder, if you will, wrapped around. So it looks something like this. Its area that it flows through is this area of the sticky note when I unfold it. And the sticky note would have the circumference. So there's a 2 pi r. And then the length of this, which, going back to your picture, your author calls it L. And as long as I have the picture, notice he calls the inner radius A and the outer radius B, and he calls the inner temperature TA and the outer temperature TB. Okay. Now, I suppose if you kind of sat down and analyzed this, you would begin to see that if you had, this whole set, we'll make a smaller inner one. And on the outside of that one, there's a little bigger one. Maybe I'll separate the two. But what I'm trying to say is the energy that flows out of this inner one then gets to the bigger one. And you can see the bigger one has a bigger radius. And so if that number gets bigger, then the temperature gradient has to get smaller as we move on out. And so you would see that inside here, the temperature change would be great, and then out here would be small as the radius got bigger, which would justify the same flow of heat energy going for it, if you let me kind of pause and read the math. But noting here that we are trying to solve for the total flow based upon the total temperature difference, let me do an integration. And keep in mind, when I say an integration, it's going to be from inside to outside. So the R is going to change as I integrate, and the temperature is going to change, but that number is not. And so when you first look at this calculus, you kind of see four little differentials. And so the question is, are you integrating what? And fortunately, those together collectively is a constant. If it helps, you could call it just a P for power flow, and then it won't look so much like calculus. And so I'll take the minus, the K, the 2 pi, and the L. And notice I didn't put the R, because I think I'm going to move the R to the other side. So the R would go downstairs, and then I'll put the dr to the other side, and then I have my dt. And so, like I said, writing this as a P kind of helps me realize that my two differentials here, one is the radius as I integrate out, and the other is the temperature. So if I start from an inner radius of A, which is a temperature of TA, and I add up going to radius B, I would now be at temperature B. And so doing this integral, this, of course, treating the P as a constant pulls out, and I would have a natural log of B over A. And so that might be the harder integration. But the math isn't real hard here. It was the concept of what to do with the math. It was more reading the math than it was doing the math. And then on this side, I have the minus K, the 2 pi L. Those are just all constants. And then I just have an integral of dt, which is T. So this would be TB minus TA. And now to solve for the power flow, whether you want to just call it P or switch it back to dq over dt, I would have something like, and I'll put the K and the 2 pi and the L, but I'm going to put that negative sign into here, so this would be the temperature of A minus the temperature of B. Or I could have just said, hey, absolute value, it doesn't really matter. But to get a positive number for the flow, I do have to have the hotter one listed first. And then I can divide by this natural log of B over A. And I think we got it. Yep, that's what they wanted us to solve for. And sure enough, we have now a nice equation that says how much does it flow. And so based upon the material we use, and of course the dimensions, so that would be the height of the water heater and the inner and outer radius of the water heater, we can figure out how much heat's going to flow out of this. And then as an engineer, we can give an estimated cost of how much gas has to do just to keep the water hot. And so all night long, the water heater has to do a little bit of keeping the water warm so that when people wake up in the morning, there'll be hot water in the water heater. All right, well, whoops, I talked way too much on that last one, but hopefully each of those were helpful in their own way, and hopefully you had enough time to kind of digest those, because those were the little tricks along the way that will serve us well in doing the homework in the next couple of chapters. And so we'll get more and more acquainted with those tricks. Bye now.